Coriolis effect, and that's due to the rotation of the Earth on its axis, and the fact that the Earth is a circle and not a cylinder, that the air has to travel at different speeds depending on where it's located on the planet. But for the opener, let's do the easy part, because okay, let's do tides first, because we did that a long time ago. Go way back. First semester. What is it that creates tides? The moon and what other major body? No. The sun. Okay, so now it's primarily the moon, because the moon is so much closer. But and we'll do tides tomorrow. When the moon and the sun are lined up, so either full moon or new moon, the tides are like super big and super low. Okay, when you have the moon and then you have the sun at first or third quarter, then you still have highs and lows, but they're not as aggressive as when they're lined up. When the gravitational pull of both the sun and the moon amplify the bulge of water that stays stationary, the Earth actually just travels through it. That's what creates a high tide and a low tide.
So, let's say you're in the middle between Europe and America, or yes, Europe. When the waves are coming, like how are they crashing out?
Wait, onto shore?
Yeah.
Okay.
Would you be able to drive far enough to see before they're actually splitting apart?
Okay, so let me get what you're asking me right. Okay, so you're talking about in the middle of the ocean, in between like where Europe and North America is, right?
Yeah.
So basically the waves try to go this way, they crash on the shore. That wave motion is caused by surface air. So you're not gonna have like a split, you're not like a Red Sea in the middle of the Atlantic because the waves are going the other way. That has to do with the atmosphere directly above the surface currents, which helps create the waves. It's the friction. You weren't here yesterday.
Well, so if you were to drive, like if you were to keep driving though, would the waves all of a sudden split?
No.
They wouldn't?
No. Would they flip? You mean do they curl over?
No, like, okay, let's say you're on America, you're going this way.
Yeah.
The waves are coming this way, right? And if you're just going that way, next time the waves are just going that way with you.
Waves go to shore from the ocean.
Mm-hmm.
You can't drive next to a wave if it's in the ocean.
You can. You can drive on a wave.
Okay. You mean surf? Okay. I'm totally confused right now. Let me ask the other question. What causes wind? How does wind happen? Why does it get gusty outside? What's happening? Don't you say something bad. We talked about this yesterday multiple times. How does air pressure go from what to what?
Low to high to low.
High to low. Okay, so what causes wind? Y'all, I'm making your CBA. It was the same stuff over and over. What causes wind is the uneven heating of Earth's surface. It causes pockets of cold, which are high pressure, and pockets of warm, which are low pressure. And yes, whoever said it goes from high to low, you are correct. All right, it's frozen. You guys can't see this. You're late today, so I'm all discombobulated. This originally was supposed to be winds and tides, but it was too much to do, and so I made it into two shorter lessons, one on winds and one on tides. I pulled ocean basins in with tomorrow, so it's like something like 13 slides instead of 11. It's not long. Most of these, it was that first one that was nasty. This one's got tons and tons of pictures in it too. So answer to the opener for the winds part. Winds are created because the Earth does not heat evenly. It has to do with the albedo effect. Is the Earth reflecting the radiation at that part, like ice tends to be colder? Or is it absorbing the radiation at that part, like the ocean, where it tends to be warmer?
This rich is water wet.
Is water wet? Technically, no, water is not wet.
Cool.
Technically, no, but when you get out of water and it sticks to your skin, the hydrogen bonding, the surface tension, the cohesive nature of water sticks to your skin, and that's what you associate with water being wet. But you don't technically have that until you get out of whatever, like the shower or pool or whatever.
When you get inside the pool, you're not wet.
Technically not until you get out.
Wait, really?
Technically, although if you're in a pool long enough, you like wrinkle and stuff, so it's obviously going across the barrier of your skin. I gotta blow my nose. This pollen is nuts. All right, so anyways, you guys distracted me. It does go from high pressure to low pressure. All I want is one tissue. I don't want 10. I want one. Gosh darn it. There. Wind will blow towards low pressure. It'll blow away from high pressure. Remember, it's going from high to low. From, bless you.
Thank you.
From a colder air mass to a warmer air mass.
Hey, what is going on right now? Everyone has allergies.
It's just for me, it's hackberry. That's the one that's in the air that's messing me up.
Mr. Richie,
Yes.
the universe was born at the Big Bang. What was before that?
We don't know. That's my answer to that. We don't know. A lot of people think it's like an interdimensional type of rebirth that happens over and over and over and over and over again, but we don't know before that. We have no recording before that, so we don't know. All right, so there are two major types of winds. We mentioned this yesterday. Planetary are very high altitude. So like when the Saharan dust comes off of Africa and like skips the ocean and then messes us up over here, it's riding a planetary wind, which is like where airplanes fly. It's not down here on the ground. What you think of as wind is local winds, storms, and like cold fronts, hurricanes, that kind of stuff. That's local. We're going to do planetary.
Sorry, can you go back?
Mm-hmm.
That, excuse me, the water is lower than the Earth's
I know. They didn't. Oh, I still have that charcoal. Hey, get it off my tooth.
Miss Richie,
What?
I don't even know we exist. Cool.
If I came over and pinched you, would it hurt?
No.
Okay, never mind.
Okay, you
You got it? All right. I swear. All right, so planetary wind is also called global winds. You do not come in access with this unless you're in a plane. Okay, this is very high altitude. They go planet wide. Okay, so planetary wind. They go in the same direction. Okay, and they also, in general, go the same speed. Now, your local winds, dependent on how different the pressures are, where the wind's trying to move from point A to point B. If it's a shorter distance with the amount of pressure change, then it's going to blow faster and vice versa. It's been a while since we've done that in isobars. So I'm not going to go over it in depth, but planetary winds first. Like I said, these are the ones that bring the Saharan Desert all the way across the ocean. And each hemisphere has got three major belts. This has changed from when I did this before, but there should be one more. All right, so we've got trade winds, we have westerlies, and we have easterlies, depending on where we are. And I should have put the map of the global wind patterns on your thing. We will eventually get into Hadley cells. Where are Hadley cells? Bless you. Tropical Hadley cells. All different kinds of winds. When we first did winds back when we were doing the atmosphere, we really only said that, a northerly wind blows from the north to the south. Like that was pretty much all we did. But we're about to go into all different kinds of winds. So northern hemisphere, you've got your trade winds, your northeast, your southeast. Notice they're both going the same direction. We have our westerlies, which are coming from the west to the east, which is why they're called westerlies on both sides. And then we have our easterlies, which are in the polar section. If you notice, they're bending the same way. So the Coriolis bends it to the right. And so it bends it to the right. And in the southern hemisphere, it bends it to the left. I know they couldn't see me pointing on it. If you were not here yesterday, that's what we talked about, like not really in super depth, but in more depth yesterday was the Coriolis effect. Local winds. This is what you think of as wind. These have abrupt changes in speed. They don't have to, but they have abrupt changes in direction too. When you get those nice, like really breezy days, and then all of a sudden the next morning it's dropped like 30 degrees, you've had a front come through. You got local barometric pressures, local temperatures, local storms that are coming through. And I just put a picture of palm trees blowing in the wind because I could. So planetary winds, very, very high altitude. Local winds are on ground level, surface level. Surface winds or local winds, they change speed and direction all the time. Planetary winds go the same direction, same speed. We just don't feel them because they're, 20,000, 30,000 feet up. Yeah, but I think you got to go to airfall. So land and sea breezes. We're going to talk about specific local winds. This is where you may have some background depending on if you've been in the mountains and on the beach. You just don't realize what's happening. But at the beach, when it's during the day, sand in general tends to be a light color. Now, your land has a lower specific heat than the water does. And so what that means in English is the water takes more time to heat up, but at night it takes more time to cool off. So during the day, the land heats up faster than the ocean. So this is warmer, lower, this is colder, higher, and during the day, things go from high pressure to low pressure. So that's why at the beach during the day, the wind is coming at your face if you're looking at the ocean. This is called a sea breeze because it comes off the sea. And some of you may not have been to the beach, but if you do go to the beach, it's literally, it's not like it's a gentle breeze either at the beach. It's a decent breeze. And then at night, the opposite happens. But it has to do with the specific heat. Land has less, heats up faster, cools off faster. Water in general, the ocean has a higher specific heat, takes more time to heat up, but it also takes more time to cool off. At night, this is reversed. So away goes the sun. The ground is going to cool off much faster than the ocean. Like I said, the water holds on to its heat. So now the land is the colder, which is the high. And the ocean is now the warmer, which is the low. And so it goes from high pressure, which is land, to low pressure, which is the ocean. And so now the wind is going from your back towards the water. That is why that happens at the beach. Some of you have been to the beach and some of you have not. So for those of you who have not, just, next time, just pay attention. Pay attention most people don't go to the beach at night unless they're drunk and doing stupid stuff. So don't do that.
Going to the beach at night's the best. That's when all the
weirdos are out.
That's when all the big fish come out. I was in Florida when we did that. We had a 20 or 30 pound stingray come up.
Really?
Mm-hmm.
That's big.
We tried catching it, but we had never been a net. It was like about this big around.
That's huge. Well, so the previous one was a sea breeze coming from the sea. This one's called a land breeze going from the beach out to the ocean. All right, now mountain and valley breezes, we're still doing local winds. This is where, not that they're hard to understand, but you may not have ever learned these. So during the day, we pull a picture up. I know these wonderful like clip art type pictures I'm putting up here, but they work. So the valley heats up, warm air rises. Okay, so it's going to ride up the face of the mountain. This is called a valley breeze. It's coming from the valley. Radiation warms the air, it must go up, it goes up the side of the mountain. And that's during the day. At the nighttime, does anybody still need anything? You still ready? I'm not trying to go too hurt. Let me check online real quick because I had two. Sorry, I'm moving it away. Check and see what's online. You got, oh yeah, let's see. Okay, I got Sarah, Erica, Mauricio, and Colton. Okay, I have everybody that's online. What's the matter?
All right. How do they know what time to put it on?
Well, I mean, the original clocks were things like sundials, so that was more of a trying to figure out essentially morning and like evening, but when was the actual time standardized? I don't know. I'd have to look it up, like who did it? Because your earliest clocks were shadow clocks.
Well, like, let's say.
Whoops.
that clock is made, that was like the first clock right there. How would they know what time to put it on?
I don't know how they figured it out.
I would use
I mean,
the
you
sun.
basically just figured out like sunrise and sunset and then just broke it into equal portions.
But then,
But I don't know who did it. I don't know who specifically did that. I'd have to look it up. That's something I actually would normally have weird knowledge on, and I don't. I don't know. Well, we used to use Roman numerals on clocks, so for a face clock, heck, I don't know. Knowing history, it was the Chinese that invented the modern clock. I don't know. All right, so anyways, so at night, the reverse happens. The mountain cools off faster. So you've got your high pressure where it's cold, and it's going to want to go down and replace and it's more dense, and so it's going to end up sinking down the side of the mountain face, going down into the valley. So that during the day, it's a valley breeze, and at night, it's a mountain breeze. There has to be a picture on here somewhere. There wouldn't be a big gap on the side. All right, so we did this a long time ago. Okay, you have two major types of pressure systems, and I'm talking more about storms at this point. It's been a long time since we've done storms. Low pressures. We use this a lot because of hurricanes. Low pressures will spin counterclockwise and pull in. Okay, the air has to go somewhere. Okay, it can't go down into the ocean, so it's forced up. And once it gets to the top, it's going to end up pushing out. Now, this is what creates the eye wall of a hurricane. This is just a thunderstorm. But where it's coming together, it is converging. It is coming together. And where it's at the top, it is dispersing. It is diverging. It's moving apart. The opposite happens with a high pressure. It spins clockwise, and it's actually pushing away. The convergence comes from the top or at altitude, if you hear it said that way, where it's pulled together and is actually pulled down. It has been a while since we've looked at one of those. I don't think I put it in your canvas. But high pressure pushes away and out. That's called divergence. Low pressure pulls in and is counterclockwise, and then up in the air, the opposite's going to be happening than what's happening on the surface. So if it's over the ocean, this helps drive waves. There's a reason why waves are higher when there's storms coming through than when there's not. It has to do with the friction of the air that's going across the surface. Okay, tropical Hadleys. There are different cells, and I should have put the other two. I know the one towards the poles are the polar cells, and then there's one in between Hadleys and polars, and I can't remember what it's called. I just know it starts with an F. I'd have to go back and look at it. We are concerned about the tropical Hadleys, specifically because of hurricane season, because the southern part of our United States, it goes through Texas, it goes basically through where I moved from, is 30 degrees. And that's the magic barrier where the hurricane wants to travel left from Africa, and then all of a sudden it crosses that 30-degree latitude and it starts to hook east. And poor Louisiana was in the crosshairs left and right last year. So a tropical Hadley cell is between, on both sides of the equator, is between 0 and 30 degrees. So both the north and the south, those are your tropical Hadleys. These are the ones that in between them are the trade winds. Faster winds used for original trade off of boats that had sails. There was a long time where we didn't have any kind of mechanized parts. But at least not that we're not hand turned. Easterlies go between 30 and the equator. Okay, so easterlies, if you go back and remember, they blow from where they're named. So an easterly goes from the east and blows to the west. If you look at the global, well, I'd have to go back and point at it, but the first two, they're both, the arrows are pointing this way. The Coriolis is not here. So if this is the equator, here's 30, here's 30, this is 0. Coriolis says, as you are looking at the equator, it curves to the left in the southern. Now you gotta sort of invert yourself. If you're looking towards the equator, it's going to divert to the right. So it goes from the east to the west, which is why they're called easterlies. The westerlies are gonna go between the next route. So both sides, 30 and 60, and then 30 and 60. And they end up curving east. I think these are the only two that's on here. Oh, no, there was one more. The polars then would be between 60 and 90. And those both curve west, if I'm not mistaken. They do. And it's just because of, it's a tie-in from yesterday, the Coriolis, these back and forth. Now, where they meet, weird things happen. And we'll get to that here in just a second. What do my coworkers want? Should be working, people. And solubility curves tomorrow are notes 45. Sorry, we're collaborating. Oops, not 35, 45. All right, doldrums. The doldrums are at the equator where the trade winds meet, and they essentially cancel out, and there's very little wind. It's like a dead space as far as really for seafaring. And then the horse latitudes are at about 30 of each, and we also have an interruption with airflow there. Between pressure bands, these belt bands, you have rapidly moving air. That's what the sailors used to bank on to be able to pull their trade from wherever to wherever. We just don't really do that much anymore. I mean, I know there's still sailboats out there, but not like the big frigates, like what you think of as like a pirate ship. Like, what are they called? Galleons, the ones that used to like do massive trade. We don't use anything like that anymore, which is sad because they're very pretty ships. So this section between the bands, that would have been be able to get you from point A to point B much better. You got stuck in a place like the doldrums, good luck getting out. Or the horse latitudes, good luck getting out. Y'all still need this one? No. I did not sand this right. All right, so this is showing you, I don't think I gave you this one. These are your Hadley cells. It does have it on here. The one above that is a Farrell cell. That's above, well, no, we actually have both Farrell cells and Hadley cells. And then the ones at the top of the polar cells. But this just shows you it's still that the warm air is rising and the cool air is sinking in all of them. You have, if this one's going clockwise, this one's going counterclockwise. Everything is still opposite between the north and the south, southern hemisphere. You've seen this before. Polar air, obviously this is only showing the northern hemisphere. High pressure wants to go to low pressure, where your warm air is coming from the equator and your coldest air specifically is from the Arctic, which is the pole.
Is that why it always rains down there?
Yeah, a lot, because the warm air can hold more moisture. Cold air is a lot drier. That's why when we have cold fronts, your lips chap, if you've ever noticed that. Jet streams, they blow from west to east. They're not on surface level. They're a ways above the surface. They will, I swear my coworkers are blowing up my phone. They still follow the high to low pressure, but they can move more. They're not like the planetary winds don't really change location. Like they have a specific path. Jet streams can change. And if you watch, not that you watch the Weather Channel for fun, but if you've ever seen like a weather broadcast, sometimes they bring these in because this will help drive the lower surface winds. The jet stream is sort of like in between planetary winds and like surface local wind.
So they follow no boundaries?
No, they do. They're just sort of pancaked in between. They just don't have a definitive path the way that the planetary winds. Planetary winds pretty much follow the same path. Here's something. Well, I had my tooth fixed and I think I got it. You know when they put well, you guys shouldn't know what a bond feels like at your age.
What?
Bond. I had a chipped tooth and the chip came out.
Oh.
The filling, whatever you want to call it. And so they just fixed it this morning. I could feel this, like, it wasn't sharp, but this thing on the back of my tooth, it was just a piece of the bond that pulled off. All right, so we have two major jet streams. We have the subtropical and the polar. Obviously, a polar jet stream is going to bring what temperature? Air.
They're cold.
Cold. Polar's cold. Subtropical would bring what? The subtropical would bring the warmer air. We got one more. Oh gosh, these, like I told you, these are a lot shorter than the first day. I'll go over what people are missing. I put in the one from Monday this morning because it locked last night. All right, trade winds. I mentioned this. Trade winds can carry dust from the Sahara. It can go up to 20 to 30,000 feet, which is airplane range. It just so happens to sort of come all the way across. Now, it's going to follow the same path as the hurricanes do. If you don't notice, they seem to all come like straight from the side of Africa and just throws hurricanes at us. So the desert from the Saharan desert, which is more central Africa, gets picked up into the, let's see, it's past the troposphere. So, no, it's not past the troposphere. It's the upper levels of the troposphere. That's the part that we live in. It's our weather bubble. And it comes literally straight across the ocean, the Atlantic, and it gets dumped here. We just had it like at the beginning of this year. We were having it, like, it was all hazy outside. It's not like you were like dust in your eyeballs or anything, but it was blocking part of the sunlight. It doesn't have to just be Florida. We've had it here. It just depends on how far it goes before it starts snowing. The troposphere is the lowest layer of the atmosphere. If you don't remember, that's the part where all weather takes place. Above that's the stratosphere. That's the part that's got the ozone layer in it that protects us from all the nasty, UV rays. Well, most of them, not all of them, or we wouldn't get sunburned. But protects us from the sun. This is just a generic, I don't even know what year this was from. I'm sure it says it on there somewhere. But you can see there's an obvious front here, but you should know by now that the general pattern on our area or on our country is it comes from the north to the south on unless it's a hurricane, and it goes from the west to the east. But here, you notice when we get storms, bad storms down here, in a couple days, they're up here. So, So in general, from our weather, it ends up riding the coast. It's specific, the Gulf Stream is right here. And so it sort of acts as a roadblock, if you will. And when the air starts pushing into the Gulf Stream, it gets pushed up and then it ends up riding up through the gyre up here. You don't need to know any of that, it says. It's, like I said, short. Let me pause this and I will tell people what they're missing. Please take advantage of the fact we have 20 minutes in here. I'm pretty sure the bells are off because they're supposed to be doing at least the paper testing for STAR. Let's hope that they don't have, because they can't do the online.